Good. Let's start today's seminar. Today's speaker is Teng Ma from Technion. We'll talk about the constructing onshore operator basis for all masses and spins. Please start.
Okay. Yeah. This is my topic of this talk, and based on this two work, and these two are my collaborate. And this is the content of my talk. I will first talk about how to construct a massless amplitude, and further talk about how to construct the massive amplitude. And then based on this method to construct the massive amplitude basis, we further discuss how to construct the lowest dimension massive amplitude, because when the massive amplitude basis is the lowest dimension, we can directly map it into the EFT operator. Then you can use this operator to do the EFT phenomenon study. And then I will give a summary. First, the massless case. The EFT field theory has a lot of application in physics, such as high energy physics, low energy QCD, gravity dynamics in actual physics, and condensed matter. It is especially useful in new physics search, such as electric precision measurement, dark matter search, and flat physics. But we don't see any new physics at cloud. This may indicate that the new physics energy scale is too high beyond our experiment. So EFT becomes more and more important to probe the imprint of new physics at the low energy scale. Generally, a complete EFT contains two parts: the renormalizable interaction and the high dimension operator. For generic EFT, in order to fully describe the low energy effects of arbitrary UV theory, this high dimension operator should be complete and independent. But in traditional field theory, constructing this complete and independent operator basis is very difficult. Generally, when construct the operator basis, some operators can be related with each other through the equation motion and integration by part. This will result in the operator redundancy. How to systematically eliminate the redundancy from the equation motion and IBP is still a problem in traditional field theory. Recently, a new method is proposed. It is the hep series technique from this paper. But this method can only count the operator number and cannot construct the explicit expression of the operator basis. So how to explicitly construct the operator basis is still a problem. Recently, a lot of progress have been achieved in onshore scattering amplitude. It was found that it is very efficient in some EFT calculation and construction. For example, based on the unitary cuts, the standard model effective field theory running can be extracted just through the true level amplitude calculation. And some operator mixing selection rule can be obtained based on the unitary cut. This selection rule cannot be easily expanded by traditional field theory. And the amplitude, the onshore scattering amplitude method is also powerful in constructing the scalar EFTs with the non-trivial soft limit. Then I will briefly introduce the onshore scattering amplitude. In this theory, the onshore amplitude are the function of the Lorentz spinors. These spinors are decomposed from the momentum matrix. This is its definition. The square spinors is the right-handed, and the angle spinors is left-handed. If the momentum pi is massive, its little group is non-billion SU2I. And the massive spinors and the massive spinors are little group SU2I doublet. This is the massive spinor equation motion. Actually it is the equation motion of actually it is the Dirac equation. This is their quantum number on the Lorentz subgroup SU2L cross SU2R and the little group SU2I. For massless case, the little group of massless spin G is the U1G. Right-handed and left-handed spinors take a negative and positive unit U1G charge transform on the little group U1G in this way. We can define these two kinds of spinor products, and they are Lorentz scalar. So we call this spinor product as a square bracket spinor product, and this is the angle spinor product. The onshore scalar amplitude generally can be expressed in terms of these two kinds of spinor product. Amplitude construction don't refer to Lagrangian. A consistent amplitude structure is constrained by the little group symmetry and unitarity. For little group symmetry, if the helicity of external massless particle G is Hg, its amplitude should take minus 2Hg unit charge of the little group U1G. If we define the polarization tensor epsilon Hg, which takes the same little group U1 charge as the amplitude, we can find that it can be uniquely expressed in this form, and this is for the positive helicity, and this one is for the negative helicity. Since the amplitude and the polarization tensor takes the same little group charge, the amplitude must be the linear function of the polarization tensor epsilon Hg. For the massive particle I with the spin Si, its amplitude should be in the 2Si indices symmetrical representation of the massive little group SU2I. That is 2Si plus 1 dimension SU2I representation. If we define the polarization tensor epsilon Si, that takes the same little group SU2I little group charge as the amplitude, we found that the polarization tensor expression is not unique and can be generally expressed in this form. This is because the SU2I fundamental representation is should real. Li is the number of left-handed spinors in the epsilon Si. The polarization tensor epsilon Si with a different integer value of Li actually is equivalent. This is because the left-handed spin and right-handed metal spin are correlated by the equation motion. Similarly, the massive amplitude should also be the linear function of the polarization tensor epsilon Si because they take the same little group charge. We found that the onshore amplitude is very efficient in construct operate basis of massless particles. It was found that when operate basis one-to-one correspond to unfactorizable amplitude basis. The unfactorizable amplitude means that the amplitude is just the polynomial of the spin products. So an independent unfactorizable amplitude basis represent independent local interaction. So its physical meaning is the same as the operator basis. So these two kind of bases should be equivalent. So I mean that the unfactorizable amplitude basis is equivalent to the traditional operator basis. So to construct the complete set of operator basis, we can first construct the amplitude basis and then map them into the operator basis. So this is the basic idea to construct the EFG operator basis through the scatter amplitude. Actually, construct the massless amplitude basis is more efficient. First, since the massless spin is very trivial, so any non-zero massless amplitude basis is automatically free of the equation motion redundancy. Second, the basis redundancy from the IBP can be systematically removed by the UN global symmetry. Here, the IBP redundancy corresponds to the momentum conservation constraint in the scatter amplitude basis. In this work, they found that the amplitude basis without IBP redundancy correspond to the basis of some special UN representation. So the complete amplitude basis can be constructed by finding all these special UN representation. And based on this theory, a complete set of operator basis can be constructed by the computer programs. Actually, this cannot be achieved by the traditional field theory. So this is a very.
Excuse me. Hello. Excuse me. Here you have a UN.
Yeah.
UN. So capital N, is it the number of particles in the scattering process?
Yeah.
Okay.
The N is the external X. Yeah.
Okay.
Yeah. So your scatter amplitude, we can fully solve the construction of the massless EFT. So this is a very big progress in the effective field theory. Next, I will briefly discuss how to systematically construct a massless amplitude basis. The massless amplitude basis structure consists of these three parts. The F part is the charge on the little group, which is determined by the helicity of external X. The G part is a little group neutral, so it is the polynomial of the minor stem variable Sij. The T part is the gauge structure, which is determined by the gauge symmetry of external X. Amplitude basis corresponds to the leading interaction of operator basis, because the next leading interaction actually can be determined by the leading interaction through the gauge symmetry. This is the physical reason why these two kind of bases are equivalent. Generally, to construct the complete basis of a theory, we should construct all the independent unfactorizable amplitude basis of any scattering process with this structure allowed by the little group symmetry, gauge symmetry, and identical particle statistic. For example, to construct the three-group amplitude basis, we found that there are only two possible scattering processes, all helicity plus and all helicity minus. and each one only has one consistent amplitude basis. And then we can construct these two amplitude bases, and we found that these two bases actually exactly correspond to these two ground operator.
Hello.
So hello, yeah.
Yes, in this last two equations,
Yeah.
the second line has, I mean, the operator for the last equation involves the Levitch-beta tensor epsilon mu nu alpha beta, right?
Yeah.
So it's a kind of a parity and P and T violating operators, I guess.
Yes, you can.
Whereas
do
the first line,
Yeah.
First line is not. So could you explain clearly? I mean, why the three positive gluon gluon amplitude is not.
Oh, yeah. Yeah. Okay. I understand. Yeah, actually, you need to combine this operator with this operator to correspond to. Actually, this amplitude basis correspond to the combination of these two operators.
Okay, I see.
Yeah,
So plus
yeah.
minus combination, something like that.
Yeah.
Okay.
You need to combine, but actually, these two the number is equivalent, is same, and just some combination. So these two EFT is equivalent.
Okay, I see. Thank you.
Yeah. Okay, yeah. The IBP redundance in the amplitude basis with n external legs can be removed by the global symmetry. UN. The UN is the global symmetry of the massless spinors of the n external momentums. The right-handed and left-handed spinors are embedded in the fundamental and anti-fundamental representation of the UN. This is their quantum number on the Lorentz subgroup and the global symmetry. Again, the N is the number of external legs of the scaling process. Based on this embedding, a semi-standard Young tableau of a UN representation corresponds to a spinor polynomial. Here are the two UN standard Young tableau. The Young diagram with subscript R and L is the Lorentz subgroup SU2 SU2R and SU2L Young diagram. The Young diagram filled with the number is the Young standard semi-standard Young tableau. Since the permutation symmetry of the Young index is correlate with the Lorentz subgroup indices, so the Young tableau can fully determine the Lorentz index contraction. For example, in the first Young tableau, the Young I's and J's index should be anti-symmetric. This IJ is the Young index. So so is the Lorentz index of these two spins. Then we can find that the two white boxes in one column in the Young tableau correspond to a square spin product. Similarly, the n minus 2 blue box in one column correspond to angle spin product. This is because we embedded the angle spin in the anti-fundamental representation of the UN. So it's the length of the column should be n minus 2. Because we use the anti-symmetric tensor to raise its UN index into the conjugate representation. Next, we will discuss how to remove the IBP redundance if a set of spinor product polynomial Fn or Fn tilde, which are the holomorphic function of n right-handed spinor or n tilde left-handed spinors. And if Fn furnish UN irreduce representation, and the Fn tutor in this kind of UN irreduce representation, this polynomial, actually this set of polynomial should be independent. This is obvious since there's no momentum factor in this polynomial, because this polynomial is a holomorphic function of the spinors. There's no momentum factor. So momentum conservation cannot appear. Momentum conservation redundance cannot appear. So momentum conservation redundance corresponds to the IBP redundance. So in this two cases, there is no IBP redundance. Here, the column number of the UN Untitled corresponds to the number of the spinor product. A column of two box represent square spinor product. A column of n minus 2 blue boxes represent angle spinor product. The shape of the white UN Young tableau and SU2R Young diagram are always same, because their indices is correlate with each other. So this is the basic property of the UN Young diagram. For the non-holomorphic holomorphic case, the spinor polynomials are generally in a UN reducible representation, like this. It was found that only the polynomial in the first irreducible representation are independent. This irreducible representation is obtained by just gluing the blue Young tableau with the white Young tableau without changing their shape. The polynomial in the other representation always contain a total momentum factor, which is 0. So in this way, we can systematically construct the complete set of amplitude bases without the IBP redundance. So next, we discuss some examples. The amplitude bases contain if the amplitude bases contain n right-handed spinors and n tilde left-handed spinors, the amplitude basis should correspond to a UN Young tableau with half n white columns and half n tilde blue columns. For example, look at the 4 massless formula amplitude basis construction. If we want to construct 4 right-handed formula basis with only four right-handed spinors, the UNs are semi-standard Young tableaus of the independent amplitude basis should only have 2 white column. Each column has 2 white boxes like this. Then we fill the number ranging from 1 to 4 into the 2 by 2 Young tableau to get all the possible UN semi-standard Young tableau. We found that there's only 2 semi-standard Young tableaus. Each one corresponds to an independent amplitude basis. For second semi-standard Young tableau, we can write down the amplitude basis expression according to the numbers permutation symmetry in this Young tableau. Similarly, in the following 2 cases, we can systematically construct all the independent bases. So an independent EFD basis corresponds to an independent local amplitude basis. The n-point amplitude basis corresponds to a semi-standard Young tableau of the following 3 types UN representation. So massless EFT construction can be fully solved by the scattering amplitude. Actually, use this method, we can use this. They can use computer programs to automatically construct all the possible EFT bases. Second, we will move to the massive amplitude basis construction. Massless operator basis construction have been fully solved by scattering amplitude theory. But for massive EFT, the operator construction problem is still solved and is more challenging than the massless case. Moreover, the EFT involving massive fields has wide application in particle physics, such as the Higgs EFT. It can describe the low energy effects of some UV theory that cannot be described by the massless standard model effective field theory. And the low energy QCD, dichromatic EFT, and low energy EFTs are all massive EFTs. And the massless EFT is not concise in describe physics at electric symmetry breaking phase. For example, generally there are a total 7 operator bases for 3 massive gauge bosons. But in standard model effective field series, there are infinite operators in this form contributed to these 3 massive gauge boson interactions. Constructing the amplitude basis of a massive field is more difficult because the amplitude basis can have both equation motion and IBP redundancy. Equation motion redundancy can be generated because the massive spinor equation motion is non-trivial. The right side of this equation is not 0. So we need to care about the equation motion redundancy in the amplitude basis. Here is some works did some primary exploration in this problem, but this cannot solve it. Next, we will discuss how to fully solve this problem step by step. Generally, a scalar amplitude with a massive external legs and a massless external legs can be factorized into these 2 parts. The massive little group tensor structure A part is only charged under the little group of massive spinors, and G is a little group neutral massive little group neutral structure, which is only charged under the little group of massless spin. And A is required to be the holomorphic function of right-handed spinors. This can always be done because the left-handed spinors can be changed into the right-handed spinors by the equation motion. We can find that on this condition, the expression of massive polarizing tensor epsilon SI is fixed in this form. It is also in the 2SI plus 1 representation of the Lorentz subgroup SU to R. Here, the epsilon SI is the polarizing tensor of massive particle I with spin SI. Since A and epsilon SI are in the same little group SU to I representation, so A is a linear function. So A is a linear function of the epsilon SI. Since A is the holomorphic function of right-handed spinors, so it cannot have the equation motion and IBP redundancy because the A is a because A don't contain a momentum factor. Massive little group neutral structure G is a function of massless spinors and massive momentum because it is neutral under the massive little group, so it cannot be the function of the massive spinors. The G part can both have the equation motion and IBP redundancy.
Sorry, maybe I missed something. So what is
Okay.
R in SU to R in the previous page? Yeah. What is R in
SU to R is a group of Lorentz symmetry. You know, the SO31 can be decomposed into, you know, SU2L cross SU2R. The left-handed subgroup and the right-handed subgroup of the Lorentz group.
Okay.
Yeah. You know, as you know, the SO4 can be decomposed, is equivalent to the SU2L cross SU2R. So this is the subgroup of the Lorentz group. SU2R. SU2R is a massive little group.
Oh. Okay. Thank you.
Yeah. Yes. Do you? So, do I answer your question?
Yeah. Yeah. Good. Please go ahead.
Yeah. Okay. Since the amplitude can be generally factorized into A and G part, we can force the construct a complete set of A basis and G basis to get a separate, and then construct A and G basis to get a set of amplitude basis. So this is the basic idea. And this amplitude, and we found that this. So again, I will repeat it. So the amplitude can be factorized into A and G part. We can force the construct the A and G basis separately, and then construct these two bases to get a complete set of M bases. And we found that the amplitude basis constructed in this way is independent without any redundancy. And we found that the A part basis can be systematically constructed by the little group Lorentz subgroup SU2R, and the G part basis can be constructed by the UN global symmetry. Then next I will explain why. Since A is a linear function of massive polarizing tensor epsilon SI, and epsilon SI is in the 2SI plus 1 representation of the Lorentz subgroup SU2R. So any A basis must belong to this reducible SU2R representation. This reducible representation is the out product of all epsilon SI SU2R representation. Here the M is the number of external external massive legs. So each A basis can be chosen to be in irreducible SU2R representation decomposed from this reducible SU2R representation. So the complete set of A basis can be constructed by finding all the SU2R irreducible representation decomposed from the SU2R reducible representation of all the epsilon SI's SU2R representation. So this is very simple. For example, the massive little group tensor structure A basis of fermion gauge boson scalar can be systematically constructed in the following. This is the SU2R representation of their polarizing tensor. The two fermion psi and psi bar and psi prime are spin one half, so their polarizing tensor are in the fundamental representation of SU2R. The vector Z polarizing tensor should be the triplet, and because its spin is 1. The scalar spin is 0, so the scalar H polarizing tensor is SU2R. singlet, denoted by the dot. We use different number to label the different Lorentz index of the different polynomial tensor. Then we can decompose the other product of this SU2R representation to get the full irreducible SU2R representation, and then they call and this full SU2R irreducible representation corresponds to 4 A bases. The A basis can be easily read out from this SU2R Young tableaus according to the permutation symmetry of this SU2R index. This is the explicitly expression of the A basis construct from the first Young tableau. We can read out the expression according to this number according to this Lorentz index permutation. So this is very easy. The G part is only charged on the massless little group. So it is a function of the massless spinors and massive momentum. Because it has the momentum factor, so G part can be both equation motion and IBP redundant. In order to get rid of this equation motion redundancy, we can force the construct the basis of G massless limit small g. The small g equal to the limit of G basis that all the massive momentums go to massless limit. The massless limit of the massive momentum pi can be written as these two massless spinors. So it is the expression of massless momentum. The small g is a small since the small g is a massless amplitude. So the small, as we said before, the massless amplitude basis can be constructed through the UN global symmetry. So the small g basis with IBP redundancy can be constructed by the UN representation, as we said before. Then small g basis can one-to-one mapped into the massive G basis by recovering the massive momentum from their massless limit. This map can eliminate the equation motion redundancy, and use the UN we can remove the IBP redundancy. We found that the G basis constructed in this way are all independent, which actually the G independence is guaranteed by the independence of small G basis. So again, the procedure to construct the G basis is like this. We can first use the special UN global symmetry to construct the massless limit G basis without any IBP redundancy, and then we map the mass limit momentum to the massive momentum to get the original massive G basis. Then we found that the G basis constructed in this procedure actually is all independent without equation motion and IBP redundancy. So this is the basic idea. One massless G basis one-to-one corresponds to the one independent massive G basis. If two massive G bases have the same massless limit, small g, it means that their difference between these two massive G must be proportional to an overall mass factor. However, this mass factor is from the must be from the equation motion. So it means that these two massive G bases should be correlated by the equation motion. So it means that only one massive G basis is independent. So the completeness of the smallest G basis can guarantee the completeness of the massive G basis. So we prove that the G bases are indeed independent if we construct in this procedure. Here is again, here is a procedure to construct amplitude basis involve massive fields. The A basis can be constructed by Lorentz subgroup SU to R, as we said before, and G basis can be constructed by first construct the massive limit G basis and then map them into the massive G basis. And then we construct the A basis with the G basis to get a complete set of amplitude basis. The amplitude basis constructed in this way are independent without any redundance. And we also prove this in our paper. Here is the example for systematically construct the amplitude basis of three massive gauge boson. Similarly as before, since the spin of the massive vector is 1, so its polarization tensor should be SU to R triplet. Then A basis can be constructed by decompose this other out product of these three triplet. Here again the different number in the box represent the Lorentz index of different polarization tensor for different particles. Then we decompose this out product of these three triplet representation, and we found that we can get 7 A basis. For the G basis, since the N is equal to 3, the length of the blue column in the G basis Young tableau should be 1. It is equal to N minus 2. So the length, so the length of the right column should be at most 1 in the G basis Young tableau. Since the A, we can see that since the A basis is Lorentz scalar, its corresponding G basis should also be scalar. This requires that one white column of the G Young tableau should contain 2 white boxes like this. But this kind of Young tableau is not a semi-standard Young tableau because the white column is longer than the blue column. So the G basis of A33 can only be just a constant. For the G basis of A42, this basis, yeah, never. The since the A42 have 2 spinors on contract. So for the G basis of A42, the G basis should have 2 white column with only 1 white box. We found that there's only 1 standard semi-standard Young tableau satisfy this constraint. So we found that the A421, A421, A422, and A423, these 2 A bases only have 1 G basis. And for the SAM analysis, we found that each A basis only have 1 G basis. So we found that there are only 7 amplitude bases for these 3 massive vectors. Actually, this conclusion is consistent with the work with this work. The reason why the number of the G bases is finite is that the minus stem variable of 3-point amplitude are trivial because the pi dot pj actually is just a constant in the 3-point amplitude. So summary, the endpoint amplitude basis involve massive particle can be factorized into A and G part. A basis can be constructed by the Lorentz subgroup SU to R. G basis can be constructed by the UN spin global symmetry. The endpoint amplitude basis can be obtained by contracting the A and G basis. Okay, now next we discuss how to map the amplitude basis into the operator basis. Now we have a complete set of massive amplitude basis AG in hand, but we cannot directly map this basis into the physical operator basis because their dimensions do not match. In other words, their polarization tensor do not match. For example, two fermion and two scalar interaction has dimension 5 operator basis. Has two dimension 5 operator basis. The first one is the AG basis, but the second one is not. This is because the polarization tensor of the AG basis are chosen to be the holomorphic function of the square spinors. The AG basis cannot contain the basis whose polarization tensor contains angle spinor. Generally, this kind of basis is a combination of the AG basis with higher dimensions. Like this. For separator, the AG basis cannot directly be mapped into the operator basis involving massive gauge boson. A and a negative polarization tensor and the negative polarization field strength F mu minus. It is equivalent to the angle spinor. The central issue is that the angle spinor I in the polarization tensor is expressed by the P square spinor in the AG basis. This makes that dimension is more high than the operator basis. So to solve this issue, we should find a complete set of lowest dimension amplitude basis that can directly map into the physical operator. The lowest dimension of amplitude basis are the basis that their dimension cannot be further reduced by the equation motion. How to solve this problem? The basic idea is very simple. We can first systematically construct a set of over redundant amplitude basis CF that can always contain a complete set of lowest dimension amplitude basis. Since the AG bases are independent and complete, we can then decompose the CF basis into the AG basis space from the low to high dimension and then remove the linear correlation CF basis according to their coordinate in the AG space. So this procedure we can always get a complete set of lowest dimension amplitude basis. So again, the basic idea is first construct over redundant CF basis, and then decompose the redundant CF basis into AG basis, and then remove the linear, since the AG basis is independent and completed. So we can remove the CF basis according to the decomposition of into the AG basis, and then we definitely can get the lowest dimension operator basis. Generally, the AG bases are complicated and are long polynomials of the spinor product because of the horizontal permutation in their Young tableaus. For decomposition convenience, we found that a complete set of much similar pH basis can be constructed from AG basis semi-standard Young tableau without the horizontal permutation. These two kind of bases are equivalent. The simple pH bases are just the monomial of spin product. This is the example to explain how to construct a pH basis of two fermion and two scalars at dimension 7. These are the two Young tableaus of A and G basis constructed as we discussed before. The H basis and G basis can be written down by just considering the vertical permutation symmetry in these two Young tableaus. Since these two bases have the two Lorentz index, so there are two different Lorentz constructions. In order to systematically construct the pH basis, we should define the convention of their index construction. The convention is that we rotate the B Young tableau by pi degrees and glue it to the H Young tableau to form a Lorentz scalar Young tableau. The two boxes glued at the same column represent the two spinors contracting together. Then all the pH bases can be constructed in this way. With the simplified pH basis, we found that any polynomial can be systematically decomposed into the pH basis, as illustrated in this diagram. The pH basis constructed from bar precision do not contain the momentum vector P1 and minus stem S23. This is the constraint from the momentum conservation and the P1 onshore condition. So in order to decompose the polynomial into pH basis, all the momentum P1 and S23 in the polynomial should be replaced by this momentum conservation and onshore condition. Then its spinor contraction pattern should be adjusted by the shorten identity to be consistent with the semi-standard Young tableau contraction pattern. Then we repeat the S23 replacement and spinor contraction adjustment until there's no S23 exists. Finally, we can get the correct decomposition of any spinor polynomial. Then we can get then the coordinate of any polynomial in the pH base space can be obtained through this decomposition procedure. Now we know how to decompose any polynomial into the independent pH basis. Now the only problem is how to systematically construct the redundant CF basis that can contain a complete set of lowest dimension amplitude bases. We found that all the possible amplitude bases can be classified by a set of massive polarizing tensor configuration. Epsilon SILI. This is SILI definition. We said it before. The Li is the number of left-handed spinor in the polarizing tensor. The different Li represent the different polarizing tensor configuration. So this is the range of the Li value. Different values of Li represent different polarizing tensor configuration. We found that a complete set of bases with one kind of polarizing tensor configuration can be constructed by the SU2R and UN Young tableau. Here we use a set of Li value to label the set of bases with one kind of polarization tensor. So the CF basis can be obtained by constructing all the sets of bases with different polarization tensor configuration. Since the CF contains all the possible bases, so the CF basis definitely contain a complete set of lowest dimension amplitude bases. So after constructing the CF basis, which contain a complete set of amplitude bases with the lowest dimension, we can then decompose the CF basis into BH basis from dimension low to high, and then eliminate the linear correlation basis. Finally, a complete set of lowest dimension can be obtained, and this lowest dimension operator amplitude basis can be mapped into the physical operator basis. So this is the whole picture to get the operator basis of massive field by the scattering amplitude theory. This is an example to construct two fermion and two scalar operator bases at a dimension 5, 6, 7. We should first construct the complete set of BH bases at a dimension 5 and 7 through the glued Young tableau. It is here is the whole BH basis. Then we construct the CF basis from dimension 5 to 7 by the Young tableau. Include all the possible polarization tensor configuration allowed by the definite dimension. We found that there are 5 polarization configuration. These are the 5 basis sets with 5 different polarization tensor configuration. The number upside is represent the polarization configuration. Then we can decompose the CF basis from dimension 5 to 7 and into the BH basis, and then remove the redundant basis. Then we get the lowest. Then we can get the lowest dimension with different dimension. We found that we get the correct 2-dimensional power operator base as we expect. As we said before, with this theory, the computer programs can systematically construct the operator basis for the massive fields with any spin. These are the four Z EFT bases at dimension 4 and 6. This is the four W EFT bases at dimension 4 construct. All these are constructed by our computer programs. Okay, so how to construct the amplitude basis involve the identical particle? Actually, we found that it can also be done systematically. For n identical boson, the amplitude should be total symmetric on this boson permutation. For the identical fermion, the amplitude should be total antisymmetric. For example, for 3 identical bosons, the amplitude should be in the total symmetric representation of the permutation symmetry S3. They should in this kind of representation. In order to get the amplitude basis in this S3 representation, we can first find the representation matrix M of this representation in the space of the amplitude basis by use the H Young operator to act on the space to act on the operator space. Then the matrix M eigenvector with non-zero eigenvalues are the amplitude correspond to the amplitude basis in the total symmetric as a straight representation. So the identical particle problem can be fully solved through this simple method. Okay, so a set of CF bases. So summary: a set of CF bases that can always contain a complete set of lowest dimension amplitude can be constructed through the SU2 across unit representation, and the lowest dimension amplitude can be obtained by decompose the CF base into the independent BH base from low to high dimension, and that remove the redundant basis in the CF basis set. Then the lowest dimension amplitude basis can be directly mapped into the EFT operator basis. Based on this method, different types of the EFT involving massive fields can be constructed by the computer programs, like the diagrammatic EFT and Higgs EFT, and also we also write a long paper to list all kind of diagrammatic EFT and Higgs EFT. So thanks. This is all my talk.
Thank you very much for the nice talk. Any questions or comments? I have one really nice question. So you use the some kind of mathless limit to limit the redundancy, right? But in the case of, for example, massive spin one particle have different degree, number of degrees of freedom. Mathless. And is it any problems for to take the limits?
Okay. Let me explain this. Actually, the G is little group is a massive little group neutral. It only the function of the massive momentum. It is not the function of the massive spinors. So the G don't have the massive little group index. So its massless limit is well defined. There is no any ambiguity. So you mean that the massive the spinor fields have different degree, but the different degree of the spinor fields is contained in the A part. The G part is, the G part don't contain any little group index. So you can have the well-defined massless limit. So this is the key point to construct the massive amplitude basis.
Okay.
You worry about the polarizing tensor, I think this is your worry. Is that right?
Okay. Thank you. Any other questions? I see no more questions, so let's thank the speakers. Thank you very much for the nice talk.
Okay.
This is the end of the seminar.